And hello everyone, this is VSA Online in Sweden calling. So it's 10 p.m. here and 8 p.m. somewhere around Greenwich. So today we have Tian with us from University of California in San Diego, and he will give a talk about application of hyperdimensional computing to federated learning. So, Yi, without any further delay, please.
I can start. Oh,
Yes, please.
okay. Yeah, hi everyone. Thanks for the introduction. My name is Tian. And I'm very glad to here to share one of our work this year. We proposed a federated learning computation framework, and we also give a comprehensive analysis and some robust communication strategy. So as we all know, I think the Internet of Things, embedding sensors and computing into various device and infrastructure, communication and collaborates data through network and cloud and edge platform. With development in recent years, nowadays IoT has been widely applied in scenarios such as urban communication, smart home, intelligence, agriculture, many scenario. Um, and in recent years, the global connector of IoT device had continued to grow exponentially. According to IoT Analyze report, there were 18 billion connected IoT devices by the end of last year, and the number of connected IoT devices is estimated to grow to 14 billion by 2030. Um, so it covers various types such as wired and circular wireless personal area network, WLAN and nearby network, as well as some private network. So, facing so many data collected by various Internet of Things device, the traditional cloud center learning framework in the past was to transfer the data to the cloud and then use larger computing power for unified training. However, a realistic problem is that many terminal like hospital use some mobile phones, smartwatch. We don't want to upload the private data to the cloud, and Mm, uh, if we transfers so many data, it also costs a lot of bandwidth and cost. Um, so federated learning is offers a new approach since it don't share the data but only shares the uh, parameters of the model. For example, as showing the figure, each client first take small steps of training with the local data, and then they just upload the parameters to the server. For the server aggregates update from all the end and to obtain a global model, and then distribute the global model to each client. So the process is integrated in the loop. This approach not only protects privacy and saves network results, but also enables the edge device to participate in the collaborative learning, getting closer to the data distribution in real scenario. Mm, However, extinct federated learning method faced three main challenges: computation cost, and the communication efficiency problem, and also the robust communication issues. So for the first communication cost, although the federated learning only transfer parameters of the model. As the number of the cleaned and training runs increase, this still brings a significant amount of the computational and communication overhead. Let me give you an example. If we want to train a ResNet 18 model in a federated learning setting with one server and 100 client, it will require 18,000 commutation after 100 training around and 110 GB data transfer. So to address these challenges, some study try to use the try to quantize the model, and some research also suggesting we can they proposed some pouring method to reduce the amount of the computation. And for the communication efficiency, the main method to solve it are to reduce the size of the model updates and the numbers of communication routes. Another challenge is the unreliable of the wellness link. During the transmission process from the client and the server network, there will be a noisy interface and fading, which can lead to bit errors and packet loss. This will affect the normal transmission and update to the model, leading to a decrease in model accuracy. Um, the common used solution at the present are to employ multiple access technology to prevent inferences and to use the error correcting codes to configure the noise. First, packet loss, they are detected and restored through the confirmation, retransformation, and retransformation. However, this brings about a lot was expensive uh, communication cost. Uh, so achieving errors-free communication requires a large a number of wireless resources, which future increases energy consumption and limits communication interface, thereby also reduce training speed and converge of the federated learning. Uh, or although exact method are try to address these three challenges, but it remains extremely difficult to effectively solve all these problems at the same time. Mm, and uh, recently, several studies prove that HDC is a very effective way to address some these challenges in federated learning scenario, because HDC is a computational method that encoding data into high per dimension vector to simulate a brain-inspired computation. It has well used in many domains, including single processing, activity classification, speech recognition, and motor sensor fusion. Compared with the traditional deep learning method, HDC is much more computational and communicative of efficient, since it enables faster and lightweight learning through the simple operates. And so therefore, HTC is well suited to run on results construction edge device. So um, based on this background and motivation, in this paper we proposed FHD. This is a new federated learning framework combining CN and HTC, it combines the advantages of the both CN and HTC can achieve significant accuracy improvement in complex image classification while maintaining a high communication efficiency. And we also provide a complete proof in the generate federated learning scenario. We prove that HTC can converge at a rate of uh, on the order of the 1 over t and analyze several of its portraits, while t denotes the number of the communication rounds. So this provides an important theoretical guarantee for HDC-based federated learning research. Next, our framework tolerates errors during the transmission, and we also analyze the performance which FHDN under the common unreliable network channel. Um, we we proposed some strategy to improve the communication efficiency and complication validate FHDN on different benchmark data sets, and the result showed FHDN has a very good performance. Mm, okay, let's take a look at the definition which the say under the federated learning. For example, if we consider one center server and n clients, uh, for these clients, each of which holds a local data set, the key uh, case client stores the embedding dataset dk equal to hkg ykg with nk equal to the absolute value of the dk. Um, this is a number of the federated labels in the specific task. We so The goal of the federated learning is to learn the global models by local data on the client side. Due to the private concerns, the original dataset can't be shared with the center server. So the training process is distributed among the various clients. Therefore, it can be defined as the distributor optimization problem. The main idea of this function is that the server want to find a best W that minimizes the weight average loss of the all client, while PK is the weight of the case client. Um, so, uh, so the goal is to evaluate to training by combining everyone's data, but instead of moving the data, we summarize the average score of the each client for optimization. For each local client, it calculates the local average training loss through this function. It's the average training loss of the key client. In other words, each device first give itself an average score. The smaller the score, the better the model is based on its own data, and then it transfers the parameters of the model to the client, and the client to also operates the process. So this is the whole uh, federated learning framework training process. Mm, in the federated learning framework, each client maintains the OHD model and participate in building a global model that solves the equation. The algorithm can be summarized as follow. At the first, it's a broadcast. The servers send the current global model WT0 to all to all client, and then it's the local training. Each client copies the global model and in its own device, and then runs the small batch uh, SGD for the e input local, uh, and each local int has the update the model W it's with its old data. In next step, they transfer the data to the server. After the aggregation, the server enters the next ground. Mm, and showing the picture, each client includes the raw data such as the image into the hyperdimension vector and the samples of the same categories into the class vector of that category. And the server average the vector from the different clients to obtain the global HDC model still uh, one hyperdimension vector per class. So next, the server sends back to the global model, and the clients replace the local model and process the next round. The figure on the right explains the local error is correct and update rulers. First, it conduct a query, use current model to match the query vector Q of the sample. If an incorrect categories is matched, it makes a correction. Correction involves the subtracting the incorrect class vector and adding the correct ones. So take the I think this process just like take the evidence of this sample from the wrong class and add it to the right class. So after multiple iterations, the classification boundaries of each class vector will become more clear. Um, Okay, so then we future analyze the potential of the function fk and delta and the delta of the fk. The first one is L smoothness. The function value has a controllable decrease. The second one is strong latest function is ball with the kernel and the operation solution is unique. The third one is the bounded variance. There is a noise even calculate grains with a small batch, but there is up limited to the noisy level. Mm, then it's the unified boundary gradients. The energy of the gradient will not be infinite either. So define key equal L divided the mu. This refers to a number of the we can reduce the E of the FW. This refers to the number of approach step that each client agrees the local in uh, each round of the federated learning. So we can view one round of the federated learning and perform gradients on all the data, but the gradients are approximate. This approximate because it has some errors, but and the errors comes from the forcings, the the random noise caused by small batch size distribution base not caused by ID, and the locomotor stepped drifter and the potential participate in sampling. Uh, through the convergent reduce the equation, we can obtain the HDC on the federated learning can achieve on the order of the 1 over T converge rate. Since the interproof process is equal to long, I just give the conclusion. For the detailed process, you can refer the appendix of the paper. So next, we first conduct a pre-experiment to observe that the comparison of the real performance of HDC and the neural network. Um, we set up 100 cleans and one server, and we train the model in 100 rounds of the communication. Uh, the baseline is four connected network with the ReLU and the Softmax. For the evaluation dataset, we use the server values, the public dataset, including absolute HCI, HAR, and face and minutes. The test result as showing the feature. So we can see that compared with the neural network, HDC has a faster convergence speed and can provide faster, earlier result. But a neural network can achieve better accuracy. This is even more evidence for the more challenges dataset. We have found that HDC is not very stable. This indicates that when faced with more complex data set, HDC has difficulty extracting the stable and effective features. Mm, some previous work also summarizes the accuracy rate of the various current HDC, including a method of running image classification task. So we can see the result show that the current HDC, including method, can't perform very well on the image dataset. The main reason is that HDC can't extract the useful features. So we are considered to address it. And we also test the different dimension of the HDC vector. Um, it can be seen that as the number of the dimension of the hyperdimension vector increase, the accuracy will also increase. However, the communication cost will also increase if we increase the dimension. So, therefore, it's necessary to consider a trade-off between the performance and the results usage. Mm, Uh, so in for this preliminary study, we can give a little conclusion that HDC converts fast, but it's not as accurate as the neural network, especially on some challenge data set. This is main because HDC has difficulty extract the accurate features. To overcome these problems, we propose the FHDNN. This is a collaborative federated learning framework that combines the CNN and HDC. It uses a pre-trained model as a feature extractor. Then output then the output are encoding into the hyperdimension vector, and then used for the federated learning training. Um, Seeing are good at learning features at the image data set with high accuracy. However, in particular application scenario, due to the limited transmission cost and the results, it's prone to errors when performs the federated learning. On the other hand, HTC can provide efficiency and robust training for distributed community in such large scale communication. So FHDNN effective combines this complement to the advantage to achieve a lightweight communication efficient and a high robust federated learning framework. Mm, FHDN employs harmonized federated learning architecture. Each claims training the model locally based on the dataset. Uh, it purposes that has the same characteristic. Then the client uploads the pairs of the training model to the center server, which aggregates all the model parameters of the client to form a unified as a global model. Mm, FHD consists of the two parts. The first part is pre-trained CNN serves as a feature extractor, and then is a federated uh, HD learner. Um, the pre-trained feature extractor is trained only once and is not updated at the runtime. So actually, it's just at the beginning, we use the pre-trained CNN model to extract some useful features, and then we uh, use the HD encoder to transfer the representation to a hyperdimension vector. And then in the federated learning scenario, we just train and update the HD vector. Mm, for the feature extractor, in fact, any CN model can be used as a feature extractor. It depends on the specific task uh, we want to address. For example, in this work, we used CLR reset model because it has a very a good performance on many datasets. CLR is a constructive learning framework that learns the representative of an image in a cell supervised manner by maximizes the similarity between different enhanced the latency of the single image. And this categories framework training on the large image dataset, so allows for transfer learning across the multiple dataset, making it ideally chosen for uh, general feature extractor. After obtaining the feature representation, we use the HD encoder uh, to transfer a hyper dimension code. Then the HD learning used the simple and highly binding and bounding the operation to update this hyperdimension vector. The goal of this configure is to avoid the transmission of the CNN and instead of training only HD learning. A high definition model is formed by the bounding or encoding a hyper dimension vector with the same class level together. The intro framework only performs the implement addition on this hyperdimension vector to carry out a binding. So the HD model is simply a set of hyperdimension vector with the numbers of class in the dataset. Then um, for the federated training process, the whole process involves two steps. Uh, it's cleaned local training and federated bounding. These two steps work in one after the other until the convergence. Each client indicates the training process using a feature extractor and on trained HD learning. Once the encoder hyperdimension vectors are obtained, the system bounding the hyperdimensional vector of the uh, corresponding class together to create class prototypes. Reasoning is accomplished by the calculating the consequent similarity measures between a given encoded data point and each cluster center. We subtract the hyperdimension from the wrongly predicted class and add it to the correct class. So then in the federated bounding framework, each client maintains its own HD model and participate to bounding a global model in a distributed distribution the process. This achieves the iterative the training procedure. Um, okay, so federated learning is often carried out on unreliable wellness channels, which can introduce the signal noisy and errors. We have designed some algorithm to enhance the robustness of the FHDN by increase the tolerance of the handling these errors. At first is noisy aggregation. Traditional wireless transmission requires the source encoding and the channel encoding and modulation, which is very expensive for the communication cost. Here we use a more economical on-code transmission strategy. We directly send out of the model parameters and the company's the number uh, symbols. In this way, what the server receives is like this, and then the server bounding the update of the multiple clients. So the single power is uh, placed by the square of the n. The noisy power is superimposed by n, so the global signal to noisy radio becomes n multiplied to SNR, which means SNR improved n times. And CNN features are first included into the D-dimension hypervectors. So the information is uh, even distribution in each dimension when uh, uh, and we can see the left image is the original symbols. In the middle image, after adding some strong gross noisy, the digital significance submerged. The right figure is reconstructed through the uh, dimension average of the HD encoding and the noise is significant supersized. Mm, uh, the next is the bit errors. Even if just one bit is wrong, the value may direct change from the uh, have a big change in the whole process. So uh, we we try to uh, use the HDC patterns in which is a general most stable. Our approach is amplificate and quantize at the same end. So as we can see this picture, if we don't uh, if we don't do it, there are if some beta is errors, uh, the scales if we don't use the quantize the R like the from 7 to the 2000 7.1 will significantly distort the similarity. So first we scale up to fill the ingrid diameter the range and then round up during the transmission. The scale down after the recognition, this effectively reduced the uh, relative the influence of the beta errors. So the radius of the same dimension becomes to uh, 1.2, which have almost no impact on the dot product. So over this first enlarged and then retracted to reduce the damage caused by beta misalignment. Mm, and the network layer errors are often uh, means for the package loss. Many detector ignores the package and directed the discard them. So the link so the large of the packet length, the more bit errors there are, the more likely to lose the packet. How to solve the problem of the packet loss? Some traditional approach are transmission by TCP, but it comes at the cost of the high latency and additional the overhead. So in this paper, we just used the UDP because it's the low latency and the low overhead. We evenly split the information across all dimension of the hypervector and even parties like uh, world field image. So the loss in some dimension only means missing just a part of the information, and the model can still work. We random to miss some a part of a dimension of the center types hypervector, and with the figure on the left shows that the learning relationship between the number of the retained dimension and the uh, and the information still in the hyperdimension vector. The the picture on the right shows that the classification accuracy curve, even after remove 18 percent of the dimension, there is still uh, approximate 19 accuracy. So therefore, we found that actually HTC is a very good robotics method for the package loss because even it missed some packet, the final result is still accurate. And yeah, although the HTC model is much smaller than the DN model, it still some pleasure on the IoT device with limited results because if we train many around on the federated learning scenario, we still need to transfer the uh, many parameters of the model. So we future studied some strategy to speed up the process. The first one is minimize the different the transformation. The core idea is no longer to upload the com complete the model, but only to show the direction of the uh, variation. This saves the bandwidth, has more stable coverage, and also it's stable for federated training under the large scale uh, scenario. And the second strategy is the cyber simply. We don't send the intermodal, only random send the portion of the coordination. So for HDC, due to its dispute the representation, it can still function even when some dimension are missing, make it particularly stable for this like, acceleration method. The last one is um, the comprehensive, we use the compressed sparse clone to store only non-zero values. So in this way, communication stores and dot per product calculation all decrease with the non-zero number. Um, well, the accuracy remain almost unchanged until this strategy. Um, so for the experiment, we use the detailed experiment to evaluate the performance of FHDN and also compared it with the classic CNN network like ResNet, ResNet 18. Um, we run the experiment on the two edge device. One is a Raspberry Pi and one is Jetson. We for the data set we use the four well-delivered data set, and we can see that for the fashion minimalist and minimalist dataset, the accuracy of FHDN in both ID and non-ID scenario is compared to the ResNet model. The accuracy rate has always exceeded 18, demonstrate that the good performance of FHD in processing complex image dataset. And on Core 14 and KLT 101, the accuracy of HDN for both ID and non-ID setup is higher than ResNet, especially and we also it's obvious that FHDN reduce the numbers of required communication routes and can converge more rapidly. For instance, FHD achieved near optimization accuracy in less than 25 routes of the communication uh, process. However, ResNet requires more communication routes, like 75 to achieve a stable accuracy level. Mm, for limited IoT device, local training is computational expensive. CN training that involves complex architecture and backbros of the operations, which are highly computations intensive. So in contrast, the HD is lightweight, has a low power consumption, and it's more fast. We compare the communication time and the energy consumption. of the FHDN and the ResNet. And we found on the recipe pack, compared with the ResNet, FHDN reduced the training time and energy consumption by 35, while on Jetson, FHDN reduced these two metrics by almost 18%. Um, for communication strategy, ResNet needed to send 3.51 GB data, while FHDN only needed to send about two uh, 2025 MB of the data. This result emphasizes that FEDN has a significant advantages over ResNet in enable faster and more suitable on the edge device. Mm, for the communication efficiency strategy, we also do some task to evaluate it, and we found for noisy, the FHDN model has very good at the processes the robustness and can maintain a high accuracy even at a low signal to noise ratio, while CNN model is complicated for ineffective. And for bit errors, we found that FHDN demonstrate a greater stable over a wide range of the, the BERI is the bit errors. And finally, regarding the package loss, FHDN has a strong robustness against the package loss and almost no loss in the accuracy, but the CNN will drop to very fast if some package is lost. To evaluate the communication strategy we also test the improvement of the final accuracy and the uh, uh, compared with the original baseline. As shown in the table, the final accuracy of the baseline model is 94%, and the final accuracy of the binary difference transfer summation is 91%. Mm, However, it offers uh, 32 for the improvement in communication efficiency, make it making it highly effective in reduce the communication overhead with the missing loss of the accuracy. So this result indicates that the server strategy we designed to enhance the communication efficiency and highly effective and have a very limited impact on the model performance. Uh, and after optimization, the communication strategy, the the cost of the FHDN was reduced by 2,112 times compared with ResNet 18, and the local communication load and the energy consumption were reduced by 48 to 192 times. Um, yeah, so in a brief conclusion, in this paper, we introduced a lightweight communication effective and highly robust final written learning framework, FHDN. This accelerates the learning speed, reduce the transmission cost, and can achieve the high accuracy in the complex image dataset. Um, and we also conduct a detailed analysis to prove that in general federated learning scenario, HDC have can converge very fast. And we also designed the server effective communication strategy, which also increased the efficiency or FHDL. Um, uh, Many experiments show that FHDL has a very good performance on the federated learning scenario compared with the CNN-based method. Yeah, so yeah, so it's thank you. Okay.
Thank you, Yi.
Yeah.
Thank you for the talk. So now I'm open the floor for questions. Maybe I can start with a simple one. When you talk about communication, so just again, maybe you can clarify a little bit. So in the HGC case, so you transmit a single vector uh, per update, right? So do you
Yes.
kind of split it in packets, or so you transmit it serially, or how do you do that?
Uh, you mean on the federated learning process?
Yes, yes.
Oh, I mean, for example, yeah, yes, for each class, just have the like the one hyperdimension vector, right? I
Mm-hmm.
mean, yeah, for example, on the image data set, we have many labels, and for one label is one class. For one class, we just have one hyperdimension uh, vectors, and
Mm-hmm.
then we update this this class the hyperdimension vectors on the
Mm-hmm.
federated learning scenario. So we don't need to um, update the like the CNN model.
Mm-hmm.
Yeah,
Mm-hmm.
yeah, and HDC is more fast. Yeah, so we can save many communication and uh, uh, the cost. Yeah.
Hmm. But then basically, I mean, if you continue this reasoning, I'm just thinking about your comparison of communication efficiency. So you say that, I mean, you are 2000 times faster or something. I mean, but if so, basically, the message is that you don't need to send all SNN layers, CNN layers. So,
Mm.
but in this case, why not to send just, for example, final embedding I mean, this flattened layer after all CNNs. So
Uh,
the one that you normally have before fully connected layer. So why don't communicate only a single vector per model?
oh, you mean, and let me try to understand. So you mean why we don't uh, send us the CN
No, I understand why you don't do that because I mean you convert CNN weights to hyperdimensional vectors. But in the same way, I mean, you could just communicate, the final activations after convolutional layers only. So
uh,
you don't need to send the whole all activations in principle. I mean,
oh, I mean, yeah, you mean, yes, you don't we don't need to send the whole thing, and we just send the one layer,
yeah,
right?
yeah.
Yeah.
So I mean, just for fairness of comparison. So
Oh, yeah, so I mean, we can't just synthesize the one layer because if we it it can't have the good accuracy on the just one layer. But if we embedding the representative to a hyper dimension vectors, and then we update the hyperdimension
mm,
vectors, it can. how to say it, the similarity is clear in
Yeah.
different class. Yeah,
Yeah. Okay.
yeah,
Thank you.
yeah.
So let's see if we have more questions in the audience.
Oh, I'm sorry. I think my spoken English is not good. Yeah, so I'm
No,
very
no, no,
nervous.
no. So you shouldn't be sorry about that. So
I
I
think
think
if
it was
anyone,
very
yeah,
understandable. So
if anyone has some confused and any question, you can email me. I will, yeah,
abs
reply very carefully.
absolutely. But maybe we still have some ideas around. So let's check. It's either too late here in Europe or too early, like in Australia. Isn't it, Rose? For questions.
Absolutely. I'm still in my pajamas.
That's right. That's right. But all right. So Tony, so that's the right time of day for you.
That's right. Yeah, so I'm trying to understand concretely what you're doing here. And it's I mean what you're doing is averaging the high dimensional vectors that you're getting from different models that are seeing different data.
Mm.
So it would, um, I'm wondering, it seems like that kind of approach would, you're averaging like some of the internal representations of the models, obviously not not just the raw pixels of the MNIST digit images or the final classification. You're averaging some kind of one of the internal representations. So there must be some types of models that this works well with and some that it doesn't. Is that right? Can you say
Oh
more
yeah,
about that?
yeah. You mean yes? Like for some maybe data set or task, it can do very well, but for some others.
No, I mean specifically for some models applied to the data set. So if you just take like the very simplest MNIST digit
Oh,
images, okay,
yeah.
so some models, if you average their internal representations when they are trained on different subsets of the data, that might work well, but I would think there'd be other models where it would just totally mess things up if you averaged the internal representations of models that were trained on different subsets of the data.
Yeah, I think yes, yeah, you are right. Yes. So for many, I mean, for some complex data set, especially for many image data set, we find HDC is not do very well. Like since I think the reason is that HDC is can't extract the useful features in this complex data set. So the performance is not good on this more challenged data set. Yeah. So the the one method to address is that we need use a feature extractor at the beginning, like it's a pre-trained model on this data set. It can extract some very useful features, and then we just transfer the representative obtained to hyperdimension computing, and then we can just update the hyperdimension computing.
Okay,
Vector. Yeah, I think.
okay. Okay. And another question I have is that that this looks to me, at least on the surface, to be pretty similar to the very interesting work that Graham Bent described in this forum a few weeks ago. I don't know if he's in the audience, but I'm wondering if he is, if that work also used this federated learning idea, or whether that's something separate.
Uh, separate, you
Yeah,
mean,
we have him here. Yes.
Yeah.
Okay.
No, so we we didn't do the federated learning in exactly the same way that's described here, but but we were doing a form of federated learning, but it was a form of supervised learning where you were sort of passing the vectors to ask the question if another agent had seen something similar. And if they'd seen something similar, then they could give you back a vector that labeled the thing that you'd seen. So the idea was you have your CNN, you convert the vector, so you've got a feature vector that's representative, and you pass that or you broadcast that and say, has anyone seen anything similar? And if they have, they might have a label for it, so they can tell you this is a cat or a dog or whatever, because you didn't know what it was. That was what we were just doing it very simply. But I do have a question actually. I'm just interested in the results you got when you were comparing training time and energy for a Raspberry Pi and for the Jetson.
oh,
Um,
yeah.
you get significantly better performance on the Jetson than you do on the Raspberry Pi. Is that because computing on the Jetson with the hypervector is more efficient, or is it that it's less efficient at using the standard sort of CNN? I can't see why you've got such a discrepancy. It's sort of uh, what is it, 4 times faster, the
Um,
training time on the Jetson, where it's only say less than 2 times faster on the Raspberry Pi. Do you know why that is?
you mean why on Jetson it's so quickly, but it's very
Yeah.
slow. Yeah, I think it's because Jetson have the GPU, so we can also use the GPU. But compared to the PC, maybe it's not powerful, but we can still use the GPU on Jetson. But on the recipe, we don't have the GPU, so we just can use a CPU, and it's very slowly.
But is it because the Jetson's better at handling
Yeah,
higher dimensional vectors than trying to do the same thing on a Raspberry Pi?
yeah. I think the Jetson is have the more how to say compare the Jetson recipe pies it's more limited. Yeah, yeah,
Yeah, it's just interesting that you've
yeah.
got 4 times faster uh, with FHDNN compared uh,
Mm.
with ResNet. It just seems well, yeah, okay. It's just
But my
interesting.
my
I
my
just
my,
don't
my,
understand
my
it.
theory, well, again, so what it looks on the surface, I don't know. I mean, how uh, whether this is like very comparable operations, because well, as I understand, the key computation in FHDNN is really update of centroids, right? While in ResNet, so it's full blown back propagation,
Mm.
isn't it? So how can I mean, is it kind of mm, is it correct assumption?
You
I mean, by the training, so you in
uh,
ResNet, so you really do back propagation, right? So you're passing gradient, so it's matrix
yes, yeah.
operations, while uh, in your approach, so it's really just vector addition.
Yes, yes. We don't, yes, yes. So just on the training process, just update the hyperdimension.
But again, so my question to you, more for discussion. I mean, for comparison, wouldn't be more fair as I mean, since in your approach you freeze the CNN layers,
Yes.
so you would do the same even for ResNet. So you for frozen CNN layers, you would train simple classifier only and compare.
Oh,
So
yes, we do the same things. Yes, yes.
mm,
On the same model, yeah, also freeze the, I mean, some layers and the training the the later layers. Yeah. So yeah.
mm, okay, okay. Let me see if we have more questions. So if not, maybe it's time to wrap this webinar up. And thank you, once again for the great talk. Thank you. And for the rest, thank you for joining this time. And we see each other in 2 weeks. So stay tuned. Thank you very much and take
Yeah.
care.
Thank you.
Thank you, Ye.
Okay. Thank you. Night. Okay.